found it. Tablet pen. All right, welcome to episode 41 of Games with Go, where we're going to finish up our shader hot loading and then move on to some more interesting OpenGL stuff. If you'd like to watch the stream without commercials, you can sign up for free if you have an Amazon Prime membership. You can subscribe to one streamer per month with that for free. And you have to redo it every month if you want to keep being a subscriber. And being a subscriber just gets you no commercials, basically. And it means I get paid a little bit, which helps me convince my wife to let me keep doing this. Okay, so last we left off, we were in the middle of doing a shader hot loading system. And so we are going to finish that up pretty quick now. So what I want to do is make a new file inside the GoGL package that we're making. And we'll call it shader.go. It'll still be part of the GoGL package. And then we're going to make a struct called shader. And that's going to be capital because it's going to be exported. And it's going to have an ID that will be a type shader ID. So a shader will keep track of its ID. And it's going to keep track of the paths to its components. So we're going to have a vertex path and a fragment path. And we're going to make a constructor for it. And it'll take, it will return a shader struct. And this should just be able to call load shader. So we'll say we should just be able to call create program, I think. Yeah, so vertex path, fragment path, and we'll get our program and our error. And if the error is not equal to nil when we're making a new shader, we're just going to panic for now. Otherwise, well, this will be the ID. All right, so that'll set. Okay, so we'll make a shader struct with the ID, vertex path, fragment path. If anyone has questions, feel free to fire away in chat whenever you're ready. Oh, yeah, this should be program ID, not shader ID. Okay, that gets us a shader, and then we'll take our code in here. The check shaders for changes code. Make it part of this file. And this is going to be our list we use to keep track of all the shaders that are open. And this is actually, we're going to make this a map. Let's see, make map. And it's going to map program IDs to pointers to shaders. All right. So now we can iterate. We can still iterate over maps just like we can lists. And we get both the key and the value when we do that. Which I don't think we need the key. We need to import OS here. Where did ORI info come from? I have no idea. It just wants a path, right? Pretty sure. Okay. So we get the time that this file was modified. Oh, we'll need to keep track of our modified date. And that is a, what was it? Time.time. We're going to delete this program info struct we were working on. This is now going to be part of our sort of our shader class type thing we're making. No. Wrong tab. Time.capital time. And we'll need to import time. And did we make a get? No, we didn't. So let's make a function to give us the modified time of a file. And we'll pull all this stuff into there, because we're going to be doing this a bunch. So we'll just return the file mod time, which is a time.time. This is just the file path. And then this can all just be get modified time, vertex path. I'm just going to call this shader. And this is the vertex mod time. We want to check both the vertex and the fragment modification times, because if either one changes, we want to rebuild the program. Okay, so if mod time is not equal to, oh, that means we need two separate modified times. Vertex modified, fragment modified. So if vertex mod time is not equal to shader.vertex modified, or fragment mod time not equal to shader.fragment modified. So if either of those are not the same, we're going to reload the shader. Basically going to redo this. And then in this case, if error is not equal to nil, we don't care. We're not going to do anything. So actually we're going to check and say if error is equal nil. Actually, let's do something. So if there is an error, we'll just print. We'll just print the error. And if there's not an error, then we'll go ahead and reset. Why is this not happy? Fragment mod time. This is shader.vertex path, shader.fragment path. Okay, otherwise, the shader's ID is going to equal our new ID. And we need to call, we need to import the OpenGL stuff. Because if we've loaded a new shader, we need to release the resources for the old shader. And we should be able to do that with GL delete program shader.id. But we'll need to do that, of course, before we override it. And we'll need to cast that to unsigned integer. There we go, you at 32. And the last thing we need to do is we need to set the mod times when we create the shader. So that will be get modified time vertex path, get modified time fragment path. And I guess to do the errors properly, we should do the typical pattern where we return the error, not just panic. So we'll return let's just return a pointer to a shader, so then we can return nil, error. Otherwise, return the shader or nil. Okay, let's give this a try in our program, Hello Triangle. So currently we're doing it like this. Now we're going to try new shader. Oh, We definitely forgot a step. We need to add this to loaded shaders. So we'll say loaded shaders ID equals this. So we need to say result is equal to and shader, store the result in the map, then return the result. Okay, so we get a pointer to our newly created shader, add it to the map, and return the results. And what this does for us is that whatever ID you get the first time you create the shader, when you call the new shader, your program code can keep using that ID over and over. But if we detect a change in the file during one of our frames, the underlying ID that's stored in the shader will be changed. But the ID that you get the shader from in the map will not. So the program thinks it's still just using the same old ID. But when we call use shader, oh, and that's something else we need to change. So this, we're going to make a version for the shader. So we're going to have function use, which will be a shader receiver. We'll get the shader. So shader is equal to loaded shaders of ID. And then we will say shader, we'll say GoGL.useProgram shader.id. Oh, we don't have to say GoGL because we're in GoGL. Okay, so now, because this is our shader, we can just call shader program.use. Oh, we don't need to pass the ID. We don't even need the map, do we? Because we can just look up our own ID. This could just be, yeah, this can just be a slice. I'm going to get rid of this completely for now. Once we have more than one shader, we'll think about how we want to store this. So we're not even going to worry about that right now. So use won't take anything. And this will become a shader receiver. And we'll take out that loop. So it's just going to check the one shader. That should all be fine. Check shader for changes. All right, let's give this a try. Let's go to hello triangle. All right, we've got a white triangle. Now let's bring up our fragment shader. And let's change it. Still white. Let's make it red. All right, there we go. And just to show that this is happening instantly, let me keep both things open at once. So I'm going to add a green component, hit save, and the color changes. Right, and this is a really useful thing. There's a lot of times when you're making a game or any kind of program where you're playing with shaders a lot, and you don't want to have to like restart the whole program, get to the same point, wait for the build to happen. So here you just change your program, change your shader program whenever you want, and at runtime automatically adjusts. So it's a really easy, a really useful system, and it's not hard to make. Right? It's just a few lines of code. And and if you were doing something like if you're releasing your game, doing a release build or something, this you would usually want to leave out. You don't want to waste the time because who knows how fast this is on every operating system. It might be fast on some, slow on others. It's probably not slow, but you would usually leave it out. It's just for development purposes. Okay, hot loaded shader system is in. So we can use this for all of our future shaders. So next up, let's move on from just a triangle to a quad. A quad is what graphics programmers call squares, basically. So recall, we talked about how if you draw something like a square, in 3D graphics, what you're actually drawing is 3 triangles, or 2 triangles. All right, that would be one way to do it, or you could go the other way. And normally you would think, okay, that's got 1, 2, 3 vertices for one of the triangles, and then 1, 2, 3 vertices for the other triangle for a total of 6. But there is a memory and speed saving technique, which is noticing that some of the vertices are shared. So really you only need 1, 2, 3, 4 vertices to make a quad. You just have to share that one and that one. So we're going to see how we do that. We use something called element buffer objects for that. So first thing we're going to do is make our 4 vertices instead of just 2. So let's see, we're going to have 0.5 and 0.5, and we're still going to have 0.0. We're not doing any depth yet, so Z we're just going to always leave 0. So let's see. Then we're going to have 0.5 and minus 0.5, and minus for both, and then minus 0.5 and positive 0.5. Okay, so I've got 4 vertices defined here. Let me just double check these are correct. Yep. And another thing we're going to do is we're going to add texture coordinates to these vertices. So this is a way of telling OpenGL that this thing we're going to draw, how you map a texture, how you map a 2-dimensional texture onto it. And in this case, it's pretty simple because it is itself a 2-dimensional thing, same shape as a texture is, rectangular or square. So the texture coordinates This is going to be the top right corner, this vertex here. So we give it a 1.0 and a 1.0. Everything usually is in OpenGL is from 0 to 1, where 1 is max, 0 is minimum. This is going to be the bottom right of the quad. This is going to be the bottom left. And this is going to be the top left. Okay, so these are texture coordinates. They're still part of the same array as the vertices. Go format won't let me format this the way I want to, but that's fine. So they're part of the same array, but they represent something totally different than this. So we got to tell OpenGL about that. Okay, so one thing we got to do is make an EBO. So we've made our, this makes the vertex buffer object. This makes the VAO. And now we're going to make an EBO, or element buffer object. So we're going to do a gen EBO function. We'll add that to our GoGL. Let's see, gen EBO. We'll define a type for EBO IDs. This will return an EBO ID. And then we'll call GL gem buffers just one, the address of the EBO, and then we'll return EBO, cast to an EBO ID. No, we're not going to do a type. Yeah, we will. So the element buffer is basically the same thing as the array buffer. What we can do, since we have the distinct types, is we can make our bind vertex array, bind buffer, I know we should do. We should just make this I think we should make all of these just buffer ID. I think it will be more confusion than it's worth trying to separate those all out. We might change our minds later, but for now it's just going to be buffer IDs. So buffer ID, buffer ID. I'm just going to call this buffer to make it more generic. Okay, I don't think that affects any of our code here. We don't have that yet. Okay. So buffer data stays the same. And now we're going to make an EBO. So we're going to call the same genbind buffer, but this time with a GL element buffer instead of an array buffer. So this time it's an element buffer. And oh, we need to make indices. So the basic idea here is we have a list of vertices here. And now we're going to have a list of indices. So we indices into this array. And this will actually be uint 32s. We do 0, 1, 3. And 1, 2, 3. So this is going to represent triangle 1. This is going to represent triangle 2. And what this means is triangle 1 will consist of the vertices 0, 1, and 3. And triangle 2 will consist of the vertices 1, 2, and 3, which will end up drawing out these two triangles. So this time we're going to need a buffer data that takes integers. So it's going to be just like this. Just like buffer data float, but we'll make buffer data int. And this is the sort of thing where you could make one function out of these if you had a language that had generics or templates or something. Everything else should be the same because a uint32 is also 4 bytes. So we just change that data type there. It's the only thing that's different. So buffer data int. And we're going to pass it element array buffer. This is the target. We'll pass it our indices. And it'll be a GL static draw again. Okay, now our attrib pointers, which tells us how these things are laid out, is a little different. So this is still 0.3 float. But now this is going to be 4 instead of 3 for the size, because we have 4 vertices. And we're going to have another vertex attrib pointer. From 1 to 2, still floats. And okay, here we actually need to pass in the size. can we just, what does it expect? It expects pointer, unsafe pointer. Let's see, how are we doing the GL pointers elsewhere? Can we do that? Oh, this just takes a regular false. Okay, it's happy with that. So what we're setting up here is for, oh, this is actually 2. We have the 2 types of data in here. We've got the vertex and the texture coordinate. And we're telling it about those 2 types of data and where they are in the array. Let's see, why is this? Oh, we still haven't used the EBO. I don't know if we need to use the EBO. Yeah, I don't think we do. So this could be a ignore the return value. Okay, so down here in the draw, we don't want to draw arrays anymore. We're drawing elements. So there's a call draw elements. And we're actually drawing six things, even though some of the vertices are shared. And we tell it that the the indices are unsigned ints. And we start at 0. Okay, let's give this a try, see what problems we have. Chat thinks that the stride should be 5 times 4 for x, y, z plus 2 coordinates. I think you might be right. I think I was actually looking at an example where I took the z out. So you may be right. Unsupported type int single 59. I don't think that was the cause of this error, but maybe. No, I think it's this pointer. I am not confident of how to pass this to the Go. Like, I can't do that. Maybe it can be first element of an array or slice. Or indices. So that'll probably run, but won't be correct. No, it's not happy with that either. Let's see if there is an example on the bindings page. How much time do we have? Plenty of time. Chat tells me there's a GL pointer offset. That sounds promising. Still unhappy with the same thing? No, new spot. Oh, it's probably the same thing here. All right. Thank you, S Smashing SF. Is that how you want me to pronounce your name? You help out a lot, so I want to get it right. Okay, so now we have a quad. And the reason it is currently a rectangle, even though we kind of defined a square here, is because it is projecting it by default onto our screen, which is a rectangle. Later, we'll learn how to do projections, which can do what we want. But this is expected. Okay, so last thing I wanted to do was make a much more interesting shader, or show you at least a much more interesting shader to give you some appreciation of how cool shaders can be. So this is one I pulled off of Shader Toy, which, by the way, is a really useful website that I'll show you real quick. They say they're in beta, but I think they've been around for like 900 years already. So that's the link. Basically, it's like a little playground. I'll just click on today's featured shader, where you can just type shaders straight into the browser, and it kind of predefines some inputs for you. Like it'll pass in time and resolution and mouse position and stuff. So you type in slightly modified GLSL syntax in here, and you can hit run, and you see your results, right? And you can like change values here and see how it changes the answer. Like what if we just take this out entirely? It's gonna get goofy probably. There, that'll do something different. All right, I've ruined it. But this is a really good way if you want to just try out some ideas and don't want to have to write a whole OpenGL program to get started. You can just play with Shader Toy. And you can also browse other people's shaders and see what kind of crazy things people have come up with. And people have made whole games, like just in the shader. Like you can see this Pac-Man video. It's pretty wild. Okay, so where is this shader? This is something I modified from Shader Toy. I'm just going to dump it in here. This is a kind of Starfield effect. And it uses simplex noise, which we've covered in a previous episode. It uses a shader implementation of gradient noise to do some nebula effects. This might just work as is. Let's try it. Okay, we're all white. Why are we all white? Text chord. Maybe because we're not passing in these uniforms. Let's try deleting that for now. still what? Are we getting any errors in the console? No. So the shader's compiling. What aren't we happy with? What's missing? Oh, you know what? This vertex shader doesn't have enough stuff in it. We need to set the texture coordinates. So let's do that. And we don't need this position thing. That will be for later. Sorry, I'm going to pull something up real quick. Vert. Okay, let's actually leave that there for now. So that array we created that has the vertices and the texture coordinates, this is how the vertex shader gets access to that data. So we're saying the first thing that we defined with our attribute pointer is going to be the position, and the second thing we defined is the texture coordinate. And we're going to make an output variable. So it's going to be a thing that our vertex programs will output into the fragment programs. Will be a vector2 text chord. So that's just an X and a Y. Why can't we just do... I think we can just do that. Okay, so this now is an output from our vertex shader that comes into our fragment shader. So now our fragment shader, each pixel that's being rendered here by this program will know where on the quad it is. It'll know the XY position on the quad. Still nothing. Why not? Text chord equals a text chord. We set the out. And we set the in. Frag color is the output. So just as a sanity check, let's try the old let's try just making it red. Failed to compile. Oh, semicolon. Okay. Yeah, red and blue. Okay, so that's working. This worked just fine. A different program I was playing with. It could be that our texture coordinates are not correct. That's probably the most likely scenario. So let's double check that. Okay, so the index, I think this should be 1 and 3. It's it's the second attrib pointer, so it's 1, and then 3. Oh no, that's just the size. Size is 2. Yeah, okay. That was definitely wrong. Still no go though. Text chord. A position. Oh, smashing, you've got it again. We did not enable it. So we have to enable number 1. There we go. Still nothing. So enable 0, enable 1. Oh, this might need to be 2 times 4 again. There we go. We're close. It's still goofy, but it's close. Let's double check our texture coordinates. 1, 1, 1, 0, 0, 0, 0, 1, 0, 1, 3, 1, 2, 3. That's all good. Float false. Item size of float. And this is what I'm least confident about. Like, I know what to do in C++, but I'm not sure what to do here. Oh, I know. There we go. Okay, so that is a little procedurally drawn star field with nebula, which is pretty cool. The next thing we're going to do, and I'll try to do this fast since we're running low on time, but we'll get it finished anyway, is we're going to be able to pass variables to our shader, which is a thing you can do, which is handy. You can pass textures and floats and ints and whatever you want to a shader. So we're going to pass in an X and a Y to our fragment shader. And we can specify that we'd like to do that. Up here, we say uniform float X, uniform float Y. So that sets up two floats that we can pass to our shader. So we're going to go to GoGL shader. Open it up here. And we're going to make a new function for it. Called setFloat, which takes in a float 32. And then we're going to call an OpenGL function called GL uniform 1F, which means uniform single float. We're passing one float to the shader. And then we need to call gl.get uniform location. First we need our shader ID, so shader.id, and then the name. Of the value that we're setting, and then the value. Wait, this is the end of get location, then we give it the value. And we need a name here. Okay, so there's a lot going on here, so let's break it down. Let's get first, the name as a C string is equal to gl.name. So that gets a C style string that's an array of bytes. The location is equal to gl.get uniform location. Unit 32. So what this says is this call looks at the shader that we're giving it, right? We're giving it the ID of this shader, and it looks at this string and it finds the location of that string. So if we passed it X, it's going to look through all the uniforms and say, okay, where does X go? Like what spot of memory does X go into? That finds the location. So then we can set it. Our value is F. So then we set that location to this value F, which is a float 32. Okay, now that we have made the helper function, all we have to do in our program is set it. And what I'm going to do for now is just say X is equal to 1.0. Let's say var X float 32. Start at 0. And then each time through a loop, we'll add a little bit to x. And then while we're using our shader program, which is important, we're going to set float x to x. We'll just set y to 0 for now. And then in our program, we'll actually use this x and y now. And this speed is actually a misnomer. This is really, it's really position. Let's rename it. Whoa. VS Code is bad about not defaulting to the selection. I guess we do want to change all of the speeds to positions. All right. Argument missing, null terminator x. Null terminator, oh. Okay, so we have to do, remember our, what was it, x00? We have to put a null terminator on our strings. The bindings don't do that for us. Now we have a moving star field. So what's cool about this is like, you got all this math going on, but our CPU is not doing anything. The only thing our CPU is doing is adding 1 to x, passing it to the shader. And our GPU is able to make this animation on our quad. And you could do the same thing on any, you could put a million triangles together into some complex shape, wrap a texture around it, and have your shader do stuff like this. All right. Any questions, chat, about today's stream, previous streams, or programming in general? I'm going to make this bigger just for fun while I wait to see if there are any questions. There you go. Now you have full screen space scene. Yeah, you can actually also change the z coordinate and like fly through this forward instead of just scrolling. You can go any direction you want. You can even hook it up to, hook up STL to the key inputs and be able to move around by pressing left, right, up, down, and so on. That's pretty cool. And this will just go forever and keep procedurally generating new stuff. The nebula will keep changing. It's pretty fun. All right, sounds like no questions. Sorry for the brief delay when figuring out this stuff, but that's kind of what's tricky about bindings to C sometimes, is figuring out all the special things to make Go stuff work with C stuff. Oh, we got it. All right, signing off. Have a good night, everybody. And I think next time we'll move on to a cube instead of a square. All right, good night.